I thought it would also be interesting to take the OCR benchmarks and look at some of the results rather than just looking at a big wall of numbers here. So you can see like some of the input data is just screenshots. And then the question is, welcome everybody to another Friday of Archive Dives with Oxen AI. This Friday, we'll be diving into the Phi-4 mini technical report, which is a pretty cool paper from Microsoft earlier this year, and it's a compact yet powerful multimodal language model that uses a mixture of LoRAs to add the different modalities. And Eric this morning from the Oxen team actually did a little query in deep research to compare Phi-4, Gemma 3, and QWQ32B, because those are kind of three of the more recent small but powerful models. And deep research seemed to think Phi-4 14 billion parameter is the best out of that suite. I don't know exactly where it grabbed all this data from, but excited to see if it actually lives up to the hype. The paper is here on Archive, and it's a pretty high-level technical report. They do get into some of the details of the training data and the model architecture. But I thought I would start with just showing you kind of at a high level how it all works. So we have this new feature in Oxen AI where you can spin up arbitrary GPUs and try out. You can run notebooks, try out different models. And so I wrote a little notebook here that will download the Phi-4 multimodal model, and we can ask it some questions as we go along. And so while that's initializing, I will give you guys a few examples of what this model is good at, just to give you some fodder for what we want to ask it while it boots up. So what's cool about this model is it can take audio or image or text as input and then output text as output. So I was just brainstorming some use cases that you could have for this. So like maybe it's trying to find brands in images. Maybe it's OCR, just like extracting text from images. Maybe it's even analyzing the chart that we had here before. You can actually put multiple frames or multiple images into the context window for this model. So you could even analyze short videos. On the audio side, you can transcribe meetings. You could have it follow commands. And I was actually pretty impressed with some of the numbers that it had on the audio side. Or you could even like have it try to write some code given a screenshot. So lots of different things that you could potentially do with this model. And so let me blow this guy up too to kind of show you how this works under the hood. And this is also our new notebook interface that we'll be rolling out soon. If anybody wants to give it a try, feel free to DM me in the Discord, and we're rolling it out to beta users. But it's just your classic like transformer auto model for causal ML. You'll pass in this Microsoft Phi-4 multimodal instruct as the model. It's going to take a second to download these model weights before we can get up and running. And it takes about 11 gigabytes of VRAM. So we'll see that printed out here. I'm running this on a A10 with 24 gigabytes. And when you look at the actual prompts that are going in and out of the model, basically you're going to have special tokens that you pass in for the images or for the audio snippets. And so you can pass in multiple images or multiple audio snippets into the prompt. And then output will be the text. So I did a little tweaking of this where you could just put in URLs into the context here, and it'll parse it out, download that audio file or download that image, put it into the context, and then we can ask questions of it. So I don't have a sense of how long this is going to take to boot up, but we'll let it go and we'll kind of hop back here once it's ready. So let's start by looking at how it does this from a model architecture standpoint. So they add different modalities to this model using a mixture of LoRa while keeping the base language model completely frozen. And in their test, this gets comparable performance to like a fully fine-tuned model on multimodal benchmarks, which is pretty impressive. And so if you look at the diagram from the paper, they kind of have two different backbones, or I guess three, one for the images, one for the text, and one for the audio. And all three of those modalities, so I know this is probably a little blurry for you guys, but this is the vision side of it. So there's a vision encoder where we're going to chunk this image up into tokens. So it's going to be like a sliding or a just little patches over the image. So you can think like 16 by 16 pixel patches that are going to be put into a sequence. And you can have multiple of those. So you could have like image one, image two. All of those tokens go through a vision encoder and a vision projector. And the vision encoder's job is to go from the raw pixels to like image embedding. Then you merge all of those embeddings, and then you have this projector layer that tries to project those embeddings into the same space as the tokens, or as the language tokens or the audio tokens. So the language tokens, we actually don't do anything. We just use the same LLM backbone that they used in Phi-4. So Phi-4 is a model that they extended that is just a language model. And so they kind of use that as the backbone for the language part. And then they do the same thing on the audio side. So they'll take like a raw waveform. I think they run it through like a fast Fourier transform, chunk that up into audio tokens. And then they have an audio projector that tries to project that into the same space as the vision and text tokens. And so then at the end of the day, you'll have this sequence here that's a mixture of text tokens, image tokens. It can alternate back and forth. So you could have like some text at the start, the image, some text after that, some audio. So you could be like, compare these two images and this audio file all in the same prompt, which is pretty wild. And so after they project all of that into the same token space, they attach two different LoRAs to the transformer blocks. So they have one LoRa for the visual components and one LoRa for the audio components. And they actually train those on separate data and then merge it into the full end-to-end model. So what's nice about that is it's kind of modular, and you can kind of add these pieces on top as you go along, and the pre-trained language model actually stays the same. They freeze the language model so it keeps all of its language performance. Okay, so this thing is fully loaded up, and I'm just going to put this into chat mode here.
Greg, there's also one question in the chat.
Can you read it out loud?
Yeah, it's so the weights for the base model are never changed with awareness of multimodality. It's awesome.
Right. Yeah. So the base language model is never changed, but they do have these like two image and audio architectures on the side, and then they merge all of that in with these projection layers. So kind of like the language model tower, if you will, never gets updated. All right, let's try sharing the whole desktop here. Can we see this now?
Yep.
Cool. Okay. So we could just do like what is 2 plus 2 to start. 2 plus 2 is 4. Great. It can do the language type things. Um, so I set this up to also take URLs in, and I set up a few test data points here. So let's just grab this one. This was a image that I made yesterday while I was setting up different um, libraries on the back end here, and I needed a different version of flash attention. Um, so if we put this into the context, I can say like extract the title from this image. And behind the scenes, this is like downloading this image, putting it into the context window, and it says the title extracted is drop the 2.58. It's cleaner. You could also do multiple images. So let's see. Do I have some examples in here? I think I do, but in the more just run this in text mode. Um, and we'll be able to see kind of what the tokens look like under the hood. Let's try this one. So here I have two images, and one of them is a black and white illustration of a crab. So it's this from one of our previous blog posts, and one of them is a cartoon of a ox, and it's this from one of our previous blog posts. And so under the hood, you can see the full prompt looks like user lists the animals in these images. I said and audio files, just in case. It puts image one, it puts image two, and then the response is crab and cow. Um, so pretty cool that you can put all of that in there. And then I have even it tested out with uh, wave files. So this is like a wave file of a cow. And we'll see what it does here. So instead of putting the image tokens, it puts the audio tokens, and it actually thought that the sound was a dog, not a cow. So not perfect. I tried it with a really hard string that is like, my name is Greg Shaninger, and this is Archive Dives with Oxen AI. And so obviously it doesn't know my name. It doesn't know how to spell archive dives, and it had a pretty funny spelling of Oxen AI. But pretty cool that you can just tie any of these modalities together, and it's an open source model that you could potentially fine tune on your data or on your lexicon. Any questions so far with that before we dive more into the paper? Cool. So let's start with the visual fine tuning. So they take a base model that is this SIGLIP 400 million patch 14 from Google. And they reference this LLM to clip paper as well. So these are just exceptions of the clip architecture that we've gone over in past archive dives. And so this is this side of the full architecture. So it's the initial vision encoder. It's a patch size of 14. So you'll be chunking this up into 14 by 14 pixel patches, turning those into tokens, and then trying to project them into the language space. And so they do this in four separate stages of training. And so the first one is they only train the vision projector on captions, trying to align the vision and the text embeddings while preserving the vision encoder. So it's a pretty complicated training process you'll see as we're going along. But what that means is they're just training this layer right here, and they have this frozen. So the first step is just like take a bunch of image text pairs and try to get the image tokens aligned with the text tokens in that space and just train this portion of the model. So often that data is like crawled from a bunch of images and caption from uh, websites where people type in what the image is in the HTML tags. Pretty standard for the clip style training. And then the second step is they do joint vision training, where the projector and the vision coder are both trained. And this is more on OCR and your just like standard classification tasks. So that's going all the way up and training this entire tower in the model. So the vision projector, the token merging, and the vision encoder. This is step two, is training this end to end, and it's on a slightly different data set. It's on more uh, things that maybe the vision encoder hadn't seen in its initial training, like OCR. Next, they train the LoRA for the language decoder. So kind of this whole end-to-end thing, uh, but just kind of on the visual side. So now they're doing the generative text from a mixture of text and image tokens. So they're going all the way down this into the token space and then training this visual LoRA on top of it. And then the final step they do is make this work for multi-frames. So not just like one image in the context, but a series of frames, a video, compare this image to that image, this kind of stuff. And they're hoping that this helps extend the context length of the model in general, and then helps with some temporal understanding of videos as well. So 4 separate training runs just for getting the visual half of this all aligned and all working. Um, and the LoRa part is just step 3 within there. So now they kind of have this model that can go from a mixture of text and images to text. And the next half is, okay, how do we get it to understand audio as well? And this is a less complicated, just 2 stages of training and pretty similar to the thing they did on the audio half, where they start by just aligning the token spaces again. Um, so they have like a large scale automatic speech recognition data set. They keep the language decoder frozen and just update the audio encoder and the projector. So they actually just do this all in one step with like some automatic speech recognition data. So that's going from audio files of people talking to text, and they're just trying to align this audio encoder, audio projector, and the token space. And then the second step is they do supervised fine tune on top of that on instruction following so that you can do interesting things like this, where you say, transcribe the audio, then translate the audio to Spanish, use separator as a separator between them, and it can hopefully follow the instructions while there's a audio tokens in the context window there. Finally, on the language model side of things, they do a last step of reasoning training. So they reference this Limo and SK1 paper that show that you don't need too much reasoning data at the end of this training to get the model to turn into a reasoning model. And so one interesting thing is, like I said, they take Phi-4 mini, which is just a language model, And that language model is already pre-trained on like 50 billion chain of thought reasoning tokens from other frontier language models. So it kind of already has some reasoning capability in the language model itself. And then they fine tune the end-to-end system on 200,000 high quality chain of thought samples, also synthetic data from, they say frontier LLMs, they don't say which ones, but I assume they're like some of the internal ones they have at Microsoft. And then finally, they do direct preference optimization on 300,000 preference samples of like this response is better than this response. And they use GPT-4 as a judge to generate a bunch of data and then generate the preference pairs. And they have the actual prompt for the judge at the end of the paper here. So if you're curious about those techniques, see if I can find it. It's a pretty long paper with a lot of citations. Uh, there we go. So they actually have um, different prompts for like GPT-4 as a judge on speech, on language, on etc. And they use it to benchmark the model in general. Cool. So that's kind of like, it's not just three stages, it's like three big stages for vision, language, and text. And then even within each one of those modalities, they have multiple steps of training. So I could imagine this is just like a uh, highly complex training pipeline and a lot of things to keep track of while you're doing it. Um, they do talk a little more about the data collection. And specifically, they talk about how they improve the data from Phi 3.5 mini. Um, so the first thing is just like better data filtering of the pre-training data that goes into Phi-4. So they build a bunch of classifiers, which we've actually seen in a lot of different papers to improve the pre-training step. And they'll categorize like the big web corpus into, hey, this is toxic. Hey, this is too obscure. This is scientific data. We might want to keep it. This is math data. And I think they said they had like 50 different categories of things that they were looking at. So they're not just pre-training on random web data. They put in better math and coding data. So they augment the original data with just like instruction-based math and coding examples. Um, and the Phi-4 technical report is really where they go into a lot of the details here on the language modeling side, but they end up with 5 trillion pre-training tokens. Um, and like I said, this is a separate paper from the multimodal paper. But if you're interested in kind of like the language modeling half of things, they talk a lot about it here. And then after the pre-training, they do post-training to add in things like function calling, summarization, code completion, and fill in the middle coding tasks, which I actually didn't try many coding tasks here. That might be a fun one to do live. Say like, write some Python code to uh, process all the rows in a data frame. Let's see what happens. But in theory, this model should be able to handle this type of task as well. I wish this module would print out the tokens token by token, but we have to wait until the whole thing is generated. Certainly, to process all the rows in a pandas data frame, you can use the iter_rows method. So here's some sample data, here's a data frame, here's it iterating over the data. So pretty cool. Even coding is built in to this model at the start. So after this, they then have the pre-trained language model, and to give you a sense of a lot of the data that they had on the visual side, it's documents interleaved with text and images, it's text image pairs like captions. There's actually a lot of synthetic data from OCR, so they have like a high quality OCR model and run that over a bunch of PDFs and like extract the charts and extract the text and um, generate just a bunch of pairs from some other pre-trained OCR model. Um, they do the same with chart comprehension. So you can think of like writing some Python code to generate matplotlib charts, and you already know the answers to the questions you might want to ask from those charts because you wrote the code to generate the images. So a lot of synthetic data there, and then a lot of instruction following SFT data. And then on the audio side of things, ASR data, like we talked about before, speech question answering data. So you can just ask a question in the audio itself, and it should be able to spit out text answering that question. Summarizing speech. So they say that this should be good at transcribing meetings and summarizing it. And then some general audio understanding, like what I tried at the beginning with putting in like a uh, cow sound or something. And they say it also works with music, which I haven't tried, but is interesting. So the evaluation was pretty impressive compared to a lot of the other state-of-the-art models. And I'll pull up the paper and zoom in a little bit so that we can see the numbers a little better. Um, So they benchmark it on the visual tasks, the audio tasks, and the text tasks separately. Um, there's a ton of different benchmarks in here, and some of them are more interesting than others. Okay, this is the visual benchmarks. So you can see they have a whole suite of data sets in here. You might have heard of MMMU, or Science QA is like question and answer from science textbooks, or Chart QA is like, can you answer questions about this chart? OCR bench is how well this model performs on OCR. And so the first column here is Phi-4 multimodal. And the last couple columns here are some of the frontier lab models like Gemini 2.0 Flash or GPT 4o. And you can see we're in the ballpark of those big frontier models with just a 5.6 billion parameter model that you could spin up on a pretty reasonable sized GPU. So this first one's kind of in between the 50s and the 60s, and we're competitive there. On the Science QA, it gets all the way up to 97, which is actually better than some of these other ones. And I think it's part of that is due to a lot of the synthetic data that they generated specifically on these like charts and graphs type problems. Um, and so I thought it would also be interesting to take one of these benchmarks, the OCR one, and look at some of the results rather than just looking at a big wall of numbers here. Um, so I had another notebook that like loaded this model, loaded the data set, and ran some examples through it. So you can see like some of the input data is just screenshots like this. And then the question is, what is the wrong answer number two? And you can see in here we have like correct answer, wrong answer one, wrong answer two. And the model correctly responded with on as wrong answer two. Um, this one is like a screenshot of an app with recipes. And the question is, what's the name of the chef who received 4.5 stars on the recipe? So it has to kind of look at this image here, uh, figure out the star rating, and then try to extract the chef here with 4.5 stars. And again, it got it right. And it's just like a username here. So pretty impressive. Like if you want to use this for some sort of, you know, screen monitoring agent or something that knows about different parts of the screen and takes different actions on it. It was actually as I was going through all of these examples, even some of the ones that I had marked false in the benchmark were just because of like silly string matching things, like capital Facebook versus lowercase Facebook, extracting time, extracting coupon codes, extracting phone numbers. So pretty versatile, and it's fun to like run this not just off on one-off samples, but on a whole data set to kind of see, you know, what it's strong at and what it's not. Um, so that's kind of like the visual half of things. Pretty competitive with the other ones, and I thought this was a fun example of how you might even continue the conversation because now that you can interleave image and text tokens, you can even follow up as you're going along. So like the first prompt here is, can you help read the image and convert it to a markdown table? And so it converted that image to a nice markdown table here. And then they followed up with which is the generation with the highest and lowest percentages. So then it's taking the output before analyzing it a little more, asking another one, can you calculate the average percentage of the four generations of the image? It does some more reasoning over that. So kind of give you a sense of how you can like chain the multimodality uh, into multiple questions. And then the speech and audio benchmarks were actually super impressive as well. So they compared this model to Whisper v3 and some of the other uh, state of the art models here. And the word error rate for Phi-4 multimodal was actually much lower than even Whisper v3, which is like just an audio model. And I think the intuition there is you already have this big pre-trained language model within there. And so like half of the problem of transcribing speech is just getting the text correct. And I think seeing a lot of speech data with a lot of text data just makes this model robust in multiple domains, kind of like we are as humans. Still can't get my name or Oxen AI though, so would have to do some more fine tuning on that. It's also works in, I think, 8 different languages here. So pretty impressive. That's why it could do like the transcribe this and translate it to Spanish. And they had a pretty interesting example of this where they put in the audio file. They say, how many speakers are in here? It responds with, there are 2 speakers in the audio file. Then summarize this conversation in a clear and concise paragraph. It summarizes it, transcribe the audio clip into text. It transcribes it, translate what the second speaker said to Chinese. And so it actually like grabs just the part from the second speaker and puts that in Chinese, and then translate what the first speaker said in French. So pretty wild that you can just do this all with one model. They did a little safety research before they released it, which is pretty common practice for these models. And overall, I think it's just like pretty encouraging that you have a model that literally just takes up 11 gigabytes of RAM. So eventually, I'm sure people will convert this to a model that you can just run locally on your MacBook, even though I have it running on a GPU here. And excited to see kind of where the small multimodal models go as as they progress. I think we're seeing more and more that you don't necessarily need these 400 billion parameter models. You just need really high quality data and data for your specific tasks. And now we're seeing that you can interleave different modalities into the same model, which is pretty exciting as well. Cool. So I'll stop there for ask for any questions. I'll also kill the recording so we can kind of have a more free-form chat, and you guys can DM me some messages here that we want to ask if we want to try anything more complex. And if you're watching on YouTube, we'll see you later.